Before we begin our map reading handout exercises, I'd like to go over some essential components on each of the USGS quadrangle maps that you'll be using. You may want to write this list down to have on hand. First of all, the title, the date of publication, and the source of the map data must be on the map. Where the map is located within a larger context, such as a state or within the United States as a whole. The scale of the map, which relates distances on the map to real Earth distances on the ground. And there are going to be two types of scale that are used on the USGS maps. One is called a fractional scale, and the other is called a graphic scale. What is the contour interval, or the amount of feet or meters between each contour line? So we'll be going over that. Which way is north? So it's very important to have direction on the map. We generally just see a north arrow, but latitude and longitude can also be used to determine directions: north, south, east, and west. There should be some key or legend noting what the colors and what the symbols that are used on the map actually mean as far as land features. Sometimes this is called cartographic notation, but generally we refer to it as a key or a legend. The type of projection, and we have already learned about projection in our lecture class, but that is also listed on the map itself. Okay, so let's go through each of these on a general map, not on one of the maps that you'll be using for your handout, but just in general, I'd like to go over these components, these essential components of USGS maps. So let's start out actually with scale. I want to go through scale a little bit with you. I did mention that there are two types of scale. There's a fractional scale and there's a graphic scale. Now, the fractional scale, sometimes referred to as a representative fraction, is actually a ratio. And on the maps that you'll be using, they will always have a fractional scale of 1 to 24,000. Now, what that actually means is that if we make a measurement on our map, maybe we make a measurement of 1 inch on our map, that is equal to 24,000 inches on the surface of the Earth over that distance. But the beauty of a fractional scale is that it is unitless, which means that you could use centimeters, measuring in centimeters, and if you measure 1 centimeter on that map, it will equal 24,000 of the same units, in this case centimeters, on the surface of the Earth. If you measured a foot on your map, that would be 24,000 feet on the surface of the Earth. So the fractional scale is very useful. We will be using that in our map exercises. The other scale that the USGS includes is called a graphic scale. And these are calibrated bars, and they're actually kind of like a ruler that appears at the bottom of the map, so that you could measure a distance between two different features and then come down to the calibrated bars. And the calibrated bars are always given in miles, and then there's another calibrated bar for feet, and then there's another calibrated bar in units of kilometers. So you have the option of using any of those units that you'd like, so it makes map interpretation and map reading much easier. So let me point out a couple of these here with this short little video clip. So when we look at the bigger map, but we want to focus in on scale here, we'll notice a scale down here at the bottom off the actual map itself of 1 to 24,000. Again, that is called a fractional scale, sometimes referred to as a representative fraction, even though it really is a ratio. So if we wanted to make a measurement of between 2 points on our map, and we came out with a measurement of 1 inch, what that actually tells us is that 1 inch on our map is 24,000 inches on the surface of the earth. We'd probably want to convert inches into maybe feet or miles, which we could do, and we probably will do in our map reading exercises. Again, using the fractional scale, we can use any units of measure. Here I'm taking a centimeter measurement on a beach, and that 1 centimeter is equal to 24,000 centimeters on the surface of the earth. So again, that representative fractional scale helps us relate distances measured on the map with real Earth distances. And just below there, and we will be using this as well in in our next map reading handout podcast, notice that we have units of miles, feet, and kilometers for those 3 different calibrated bars down there, that graphic scale that is also on our USGS maps. Okay, a little bit on contour lines. So contour lines represent points of equal elevation above sea level. Because we're talking about land areas, most of the time, there are some exceptions, but most of the time, all of these elevations are going to be above sea level if you're on land. Now, the contour lines are shown in brown. So if right here is a contour line that has a value of 300, and this happens to be in units of feet, it could be in units of meters, but I happen to know this is 300 feet of elevation above sea level. So if you were to walk on the ground where this line is, you would maintain an elevation of 300 feet the entire time. So that one line connects all points on land in this area with 300-foot elevations. The spacing or interval, I should say the interval, the amount of elevation change between each contour line is indicated on the map, and I'll show you where that is in a moment. But before we look for where they tell us what the interval is, the amount of elevation change, we could actually figure it out ourselves. And what's going to help us do that are our index contours, these darker, thicker, bolder lines. So notice that the 300-foot contour line is a bit thicker and a bit darker than the contour lines above it and the contour lines directly below it. The 200-foot contour line is also a bit thicker than the other contour lines around it and darker. So these are known as index contours, and they do indeed have a value noted on the line. So this is a 300-foot index contour line. This is the 200-foot index contour line. But what if we wanted to know what this elevation is of this contour line, or what is the elevation of this contour line, or this one, or this one? How could we figure it out? Well, we know that there's a total of 100 feet difference from between these two consecutive index contours, right, from 200 to 300 feet. And we know we have 1, 2, 3, 4, and then the 5th line representing the total of 100 foot of change. So we could maybe make a guess that 100 divided by 5 is 20 feet. So let's see if that would work. You can try this out on other maps yourself. So if this is 200 feet, then we know we're going uphill here towards 300 feet. So this line here has to be 220 feet. This one would be 240, 260, 280, and then 300. So indeed, the contour interval on this map is 20 feet between each contour line. The index contour interval, however, between two consecutive index contours is 100 feet. Okay, so every single line represents 20 feet of change of elevation, but between our index contours on this map, and it may be different on the maps that you're going to be using for your handout, but on this map, the index contour interval is 100 feet from one index contour to the next. The spacing of contour lines on the map tells us a lot about the slope of the land, what the terrain of the land is like. So on the left here, we have some contour lines that are spaced very, very closely together. And on the right, we have a map showing contour lines spaced fairly widely apart, at least in this area of the map. So what does this tell us about the slope of the land? What does this tell us about the terrain of the landscape? When contour lines are spaced very, very closely together, there's a lot of change in elevation over a small distance. And that indicates that the slope of the land is steep. So when we have close spacing of our contour lines, this indicates a steep slope. Over here, where we have wide spacing between the contour lines, it means that the elevation is changing much more gradually over a distance. And so that wide spacing indicates gradual slope. So these relationships between the spacing of the contour lines and what the landscape is actually like is a nice quick indication. So when you see contour lines close together, think steep slope. When you see contour lines spaced widely apart, think it's kind of flat. It's kind of a gradual slope, okay? And we'll be practicing this in our handout. Couple of other things. Here's something that I call the rule of V's. So notice that the contour lines, first of all, we have some water in here. That blue line is representing a little creek. So the contour lines around that creek seem to bend sharply when they cross the creek. So say this particular elevation was 200 feet here. So it sort of, that 200-foot contour bends around, okay, as do all of the other contour lines as well. And the shape that they make, that general sort of bent shape there, looks a lot like the letter V. So we call this the rule of V's. When we see these V shapes, these bending, these sharp bends of our contour lines, particularly around a water feature like a creek, that indicates that this is indeed a stream canyon or a valley feature. So we can look at our map, and when we see those V's, we have a sense of what the landscape looks like. Another shape that contour lines make are these sort of closed circular loops. Sometimes they look like the letter O, but they're always these closed loops, and they're kind of nested together with the smallest loop in the center going outward to the largest loop. We call this the rule of O's. And the rule of O's basically indicates that when we see these circular loops going on, these nested circles, that is a hill or a peak or some kind of a mountaintop. And the smallest circle in the center represents the highest point. The largest circle at the base represents sort of the lowest point or the lowest portion of that hill feature. So we'll be practicing this again in our map exercise. Lastly, benchmarks. Not every single contour line has been ground truthed or ground surveyed. There's a lot that goes into the accuracy of these contour lines, but one of the ways that we can ensure that the contour line elevation values are really accurate is by going out on the ground and actually conducting some surveys. So every once in a while, there'll be a particular point that can easily be surveyed and ground truthed, and we call it a benchmark. And on the map, you're going to see sort of a little crosshairs here at the location of the benchmark, and it'll say BM for benchmark, and it will give the actual elevation of that benchmark. Now, what this would look like on the ground, if you actually went out here to this portion of the landscape, you'd see something like this installed maybe in concrete if it's a road, maybe into a rock in this case. And these are pins. They're survey pins. They're installed to stay for as long as is possible by weathering and erosion. But these pins, these benchmark pins, are put in there to stay for a very long time because they're very important points that can be put onto maps, that can be surveyed and ground truthed, and that really help with the accuracy of the topographic maps. So when you see these around, as you're kind of living on the surface of the earth, you're probably going to come across benchmarks every once in a while. And just know that that's a surveyed point. We'd never want to mess with these. We want to maintain them. I think it's actually a federal offense to remove or damage these, because they are a lot has gone into installing them, and they also relate to our map data. So we want to take good care of our benchmarks. Okay, so let's bring all of this together by pointing out these essential components on the maps themselves. Again, this is not the maps that you'll be using for your handouts, but they're very similar. They will all have these essential components on them. So starting out, just sort of looking at the map, the whole map, we want to first focus in on the title of the map and the date of publication. So notice that the title and date are generally in the lower right-hand corner. You'll also find the title in the upper right-hand corner, but here we have Santa Cruz, California map. It was produced in 1954 and photo revised in 1994. The source of the map data, well, we all know that these are published by the U.S. Geological Survey, but if you didn't know, you want to look down in the lower left-hand corner. It does indeed say produced by the United States Geological Survey. And because it has some ocean area on it, there's some other governmental bodies involved in the publication. Where is the map located within the state of California? If you didn't know where Santa Cruz was, that black box represents Santa Cruz on the state as a whole. The scale of the map, of course, we have two types of scales as we've discussed. Here is our fractional scale. There's our 1 to 24,000 ratio that we've looked at already, and then our graphic scale below it. Our graphic scale, of course, those three kind of rulers showing miles, feet, and kilometers. And that is indeed a calibrated bar. You can use any units that you like on those calibrated bars. The number 1 there says 1 mile. The interval of the contour lines, you can try and figure it out yourself, but the map maker does indeed state it, the contour interval here of 20 feet. And the direction. So we have which way is north. So the star at the top represents true north, which is pointing essentially to the North Pole. That's where all of our longitude lines all intersect each other. The MN right there stands for magnetic north. And as we've learned about in lecture, the compass needle doesn't actually point to the North Pole because that is not the magnetic, our magnetic field isn't centered around the North Pole. It's slightly in sort of eastern Canada, so it is offset from our true north. And because of where we're located on this map of Santa Cruz, California, there is what we call a magnetic declination of 15 degrees to the east. So you'd need to account for that if you're using a compass and this map out in the field to do orienteering or hiking. If you're not on a trail, then you would want to be aware of how much difference there is between your compass needle and true north. The third north on here, of course, is grid north, and that has to do with the markings on the edges of the map that you can use to grid your map into small little boxes. The grid lines or the grid ticks don't point to precisely true north, and they certainly don't point to magnetic north. They're a little bit closer to true north on this map, but again, they're not exactly the same as our longitude lines and our latitude lines. So speaking of latitude and longitude, these can also be used to help us with direction, because of course we know that all longitude lines point north and south, and all latitude lines point east and west. So on each of the corners of our maps, we are going to have both the latitude and the longitude listed. Now, latitude lines run horizontally on these north-oriented maps. So the latitude here in this northeastern corner has a value of 37 degrees 00 minutes. So as we travel across the map, if we're on that parallel of latitude, the latitude value should not change as we go to the northwest corner. So we started out at 37 degrees in the northeast corner of latitude. Let's see if it's still 37. It is indeed 37, but you might notice that the longitude value did change. Now, longitude lines, because they run north-south, if we go down to the southwest corner, just straight down on a longitude line, notice the value of longitude is the same as it was in the northwest corner. But the latitude has decreased because we've gone towards the equator. Again, heading over to the final corner, the southeastern corner, latitude has stayed the same there, lower value than it was in the northeast corner, and longitude has decreased towards Greenwich, England. Finally, a key or legend. On our topographic maps, we're only going to see road classification noted as a small legend, but we're not going to see the full legend of what all of the different symbols and colors on our maps mean. The reason that the USGS does not produce a full legend on each map is simply there's just too many features, too many colors to print on every single map. So what the USGS does is it prints a separate legend, or full cartographic notation. You can find this legend in the back of your textbook. It's one of the appendices, and you can also download it for free from the USGS Map Store, which I went over in the previous podcast on map materials. I would just like to point out a couple of general rules of thumb about some of the colors that are used on the maps. So all of our contour lines are going to be in brown, as we have seen. Hydrographic or water features are going to be in the color blue, whether it's frozen water in a glacier or whether it's liquid water in a stream or in a marsh or in the ocean. Vegetation features, whether it's forest or maybe a vineyard, is going to be in green. But of course, we're going to have lots of different symbols in the color green to represent many different types of vegetation. Cultural features, such as roads and buildings, are generally in black or red. And because our maps are updated regularly, we call these photo revisions now because we actually take aerial photographs to update our maps. And those photo revisions are in the color purple. Urban areas or areas with very high density of buildings and development are shown with sort of pink tinting. So those are some general rules, but of course you need to take a look at the full legend, and here's just one page of the full legend just showing some of those colors. So here's some of our variations in vegetation, variations in water features, lots of different types of water features. So you'll have a look at the full legend when you download it for the map reading exercise. Okay, that concludes our overview of the essential map components.